Hi everyone, can you hear me? Can you hear me?
Yes.
Okay, thank you. Okay, and welcome to the wind tunnel experiment. This one is our wind tunnel. Okay, so firstly, so sorry about the last session last week. There are some technical issues, so we can't run it. I couldn't run it last week. So that's why we have an alternative one today. Okay. And as I know, some of you start with the lab 2 already. So maybe the videos on the Canvas and the lab note are enough. So that's why you see today there's only few students, only 1, 2, 3, 4, 5, 6 students. Okay, but that's okay. So today I will introduce a little bit about the test rate, about the requirement of the lab report 2. And if you have any question, you can ask me. Okay. Okay. So firstly, this one is the lab note. The lab note. Okay. You can download this one on the Canvas. And this one is very important. Okay. All information you need, you can find this one. You need for lab 2, you can find this one. It's very important. Okay. And similar to lab 1, similar to lab 1 internal flow. In the lab 2, we have 2 parts, part A and part B. Okay. Part A you see for circular cylinder with pressure tapping, and part B for other objects, including circular cylinder without pressure tapping. Okay, we have 2 parts, part A and part B, similar to lab 1. Okay, and in the next page is some pictures of the wind tunnel. And so, and firstly, I will introduce about the test system. That's it. Okay, let's see. I show you here. Okay, this one is the wind tunnel. Okay, we have airflow in here. The big one here. Airflow in and go through a chamber. In this chamber, we have a cylinder. We have hydrostatic tube. I will talk about the devices inside this chamber later. And after that, airflow out here. In here, we have a fan. Okay. In here, we have the control system. Okay. And you see in here, we have PC mode and local mode. This means we can control the speed here. Or we can use the PC to control the mode. Okay. And now I use PC mode to control the system. Okay, PC mode. And here, this one is the lab note you have on your DS on the Canvas. And in page 3, you see the test system. We have airflow in here. And after that, we have a pitot tube. Pitot tube is this one. I will show you the pitot tube. This one is the pitot tube. Okay, the pitot tube. And in the pitot tube, you see, we have 2 signals. One is a static pressure and one is total pressure. Okay. And we have a different pressure transducer here. We have this one is static pressure and this one is total pressure. And in the other side, we have a transducer. Because this one is fluid flow. In fluid static, we only have pressure depends on the position. If we go up, pressure increase. Sorry, we go up, pressure decrease. We go down, pressure increase. However, in the fluid flow, besides the static pressure, we have dynamic pressure. Dynamic pressure depends on the moving fluid. Okay, and the total pressure you have here equal to static and dynamic. So you, from the different pressure transducer, you will have delta P is the pressure difference between total pressure and static pressure. And the pressure difference between total and static is dynamic pressure. So from the Python tube, you will have dynamic pressure in this chamber. Okay, dynamic pressure. After that, you have here is the test objects, or you have a cylinder. Okay, in this cylinder, we have 21 holes or 21 pressure tapping from number 1 to number 21. Okay, you see this one is a cylinder. And we have 21 holes on the half of the cylinder, with hole 1 here on the half of the cylinder and hole 21. This one is hole 21. Okay. And from 21 holes, you see in one hole, you have 2 signals. One is pressure inside the hole, and the green one is free stream pressure. And we have another different pressure transducer here. It means from this one, you will have pressure difference between pressure inside the hole 1 and pressure in the chamber. Okay, in the chamber. And because we have 21 holes from 1 to 21, so we will have 21 pressure difference. Okay. And here I will show you the free stream pressure or pressure inside the chamber you have from this one. And one hole, you have one yellow line. Okay. And in the other side, you will have a transducer to compare pressure between the yellow line and the green line. Okay, so we will have the pressure difference between 21 holes and the pressure in this chamber. Because the streamer strict, so we only have 21 holes on the half of the cylinder. So, but in the bottom half, the pressure is the same. Okay, the same. 21 holes on the half of the cylinder. I will show you in the other side. You can see the here. You have 21 holes and 21 yellow line. One yellow line is show you a pressure inside one hole. This one will be compared with the green one is the pressure in this chamber. Okay, so you will have the pressure difference. This and airflow out here in the right hand side. Okay, and as I said, we can use the PC to control the system. And this one is the control system. Okay, we have in this screen we have 21 holes, so by 21 column from 1 to 21. Okay, from 1 to 21. And in the right hand side we have room pressure, room temperature, total force. As you know, in fluid dynamic, because we have fluid flow, so when we have fluid flow, we will have the resistance between fluid flow and the object. For internal flow, the resistance is shown by the pressure drop, is all up 1. Okay, resistance is shown by the pressure drop. But for the external flow, for example, you have this cylinder, airflow over the cylinder. Okay, so the resistance in this case will be shown by the force. When we have airflow, we have a force applied to this cylinder. Okay, and this force we call is drag force. Okay, and total force here will be equal to drag force and pressure force. Okay, because as you know, when we have airflow, pressure on the front and on back of the cylinder will be different. When we have pressure different, we will have a force applied to this cylinder. It is pressure force. Besides the pressure force, we have drag force. Okay, and total force will be equal to drag force and pressure force. And pitot-static tube on the screen. Pitot-static tube, as I show you. Pitot-static tube. Yeah, is dynamic pressure. P total minus P static is dynamic pressure. Okay, so from this one, you will have dynamic pressure in the chamber. Okay. Here, this one is actual fan speed and set fan speed. Set fan speed will be used to set the fan speed, and you will collect data when the actual fan speed close with set fan speed. Okay. So I will try to test at one fan speed for you. Okay. For example. Sorry, it's hard for me to control everything. Yeah. Okay, so now I close the chamber and I will test. For example, I test this one at 1000 RPM. 1000. Okay, you see the actual fan speed increase until the actual fan speed close with set fan speed. And you will see the left hand side. The pressure, the blue column is changed. You see, for example, for at 0.1 to let me see, 0.6 or 0.7, the blue column is positive. It's positive, it means pressure inside the 0.1 higher than pressure in the chamber. Okay, higher than pressure in the chamber. And from 0.8 to 0.21 is smaller than pressure in the chamber. Okay, it's because of 0.1 airflow directly in the 0.1, so pressure in the 0.1 will be higher, okay, than other point. So you have 0.1, 0.2, 0.3 to 0.7 is positive, and after that it's negative. And to find the pressure inside one pressure tapping, for example, at 0.1 now is around, you need a ruler, and it's around 30 Pascal. Okay, it means now at 0.1, pressure inside 0.1 is higher than pressure in the chamber, or free stream pressure is 30 Pascal. Okay. So that's a little bit about the test system. Do you have any question about this test system? The test suite? Do you have any question? Do you have any question? Do you have any question?
No.
No? Okay. So, as I said, in lab 2, you have to pass part A for circular cylinder with pressure tapping, and part B for other objects, including circular cylinder without pressure tapping. Okay. So this table is for part A. Part A. Okay. In part A, we have 21 pressure tapping. 21 pressure tapping. Okay. So for each group, you see here, let me see. It's not here. Each group will collect data at 3 fan speed. You can choose 3 fan speed, 3 out of 5. Okay. But however, on the canvas, as you know, I give you the data already. Okay. For example, I will try at 1400. Okay, 1400. Try it at 1400. Okay, for example, at 1400 now, you see in this table, you have ambient temperature is now ambient temperature is 22.3 Celsius. You have ambient pressure is 101.25 kPa atmospheric pressure. Okay, you have fan speed for 1400. Isotope you have here is around 62.9 Pascal. Our dynamic pressure is around 62.9 Pascal. Okay. You have the force. Total force is 7.29 Newton. Okay. And after that, you have pressure at 21 pressure tapping. Okay. For example, at point 1, you will have 50. You have 50 for point 1. For point 2, you will have around 60. For example, you write down here is 60 from 1 to 21. So you will have pressure in 21 holes or 21 pressure tapping. Okay. In 21 pressure tapping. And open in here. This one, so you will have X group with 2, 3 pictures on the data. The data says I sent you already. Let me see, open it. The data, okay. So in here, you for part A, you have the data at 1400, you have 1600, you have at 1800 and 2000. You choose 3 or 4, okay. 3 or 4 for the calculation. And the calculation, you follow the instruction here. For example, for part A, you have 5 steps: pressure drop, friction drop, Reynolds number, drag coefficient, and compare CD from this experiment with CD from elsewhere. It's similar to lab 1. Maybe I turn off this one. It's too noisy. It's similar to lab 1. For lab 1, you find delta P, compare delta P. Okay. In this one, you find CD. CD is a drag coefficient. Maybe you will study about external flow next week. Okay, drag coefficient, and compare drag coefficient from experiment with CD, maybe from textbook, from internet, whatever. Okay, and how to find CD? We give you very detailed sample calculation here for part A. Okay, for part A, circular cylinder with pressure hole. In here, because we have 21 holes. Okay, so you need to find the pressure or the force in 21 holes here. Maybe you can use Excel to do this one. Okay, and after that you have total force or drag component. Follow this one. It's very detailed. Okay, for part A. For part A. CD for part A. Do you have any question?
Oh,
part A.
There is a sample. Is there a sample calculation now? Because when I downloaded the document, there wasn't anything like that. Okay.
Yes, you see the data with internal experiments. You have sample calculation in here. At the end of the data system.
Yeah, I thought. Okay. Yeah. Okay. I'm sorry.
You can double check. You can double check if you can't see it. Email me.
Okay.
Yeah. Okay, the sample calculation here for part A. It's very detailed.
That's good because I was a little bit confused with the formulas. The formulas in written and handwritten, but with the
the formula here. You have the formula here. Because you have 21 holes, so we divide to A, B, C, D, E, F. Okay, so you will have equation to find drag force between A and B, B and D, D and F. Okay, and you will apply the equation to this table. This table. Okay.
Okay.
Do you have any question?
Well, I will have later when I start doing the calculations. I will do that this afternoon. Maybe I text you. Yeah. I write you an email if I need something. Thank you.
Yeah. So email me if you have any question when you start with the calculation. Okay.
I have a question.
Yep.
So on the cylinder, there's 21 hoses. I was just wondering, are you able to twist it and reorientate how those hoses are positioned?
Yep. Yeah. We have 21 holes.
Yeah.
And let me see. We have airflow in this way. Okay. So hole one is this way, directly inside hole one, and in the other side, hole 21 on the half of the cylinder. We only have 21 hole on the half of the cylinder. You can see. Yeah, you see.
Yep. And you're able to rotate that?
There we have hole one, hole two,
Yep.
3, 4, 5. Okay, in each one hole, you have a pressure, one pressure. It's pressure at this point. Okay, and because we have 21 pressure, so from 21 pressure, we can find the pressure applied to the half of cylinder. And similar for the bottom half, because the swimmer sheet, so the bottom half is the same with the up one, the 21 holes. Okay.
Yeah.
Yep, 21 holes. Yeah, with air flow directly in hole one. Yeah.
And you're not able to rotate that?
No, we don't.
Okay, it's
no,
fixed.
no,
Thank you.
That. Yeah.
Thank you.
Okay. So let me see. For part B, they're about to settle data for Excel. We want to choose one out of two. Okay, for part B, I will talk about part B now. Do you have any question about part A? Any question about part A? Before we have 3 sets.
No, for now.
For part B. Okay, so for part B, for part A, we have the cylinder. And in the cylinder, we have 21 pressure tapping. Okay, that's why the part A we call is for circular cylinder with pressure tapping. Okay, but for part B, for other objects, including circular cylinder without pressure tapping. And for part B, it's 4. Okay, here we have 5 objects. We have a circle, we have square, we have diamond, raindrop facing forward, and raindrop facing backward. Okay, this one is our system. And in part 2, for example, for first one is the cylinder, a circle. Okay, we will use this one to cover the cylinder. When we cover a cylinder, we have a new cylinder, but without pressure tapping, no pressure tapping, because 21 pressure tapping is covered already. Okay, so we have a new cylinder for part B. Is the first one circle, first one circle. For the second one, square. Square, we will use this one to cover. Here we have a square, set square. Okay, and first one is a diamond. Here we have a diamond. Okay, after that we have raindrop facing forward. We use this one, so airflow this way, raindrop facing forward. Okay, and raindrop facing backward, we have this one. Okay, raindrop facing backward. So for example, we will run with raindrop facing backward. Okay, we will run with raindrop facing backward. Okay, for example, at 1600. At 1600. Okay, So you see now, because for part B, we use raindrop facing backward to cover the cylinder, cover 21 holes already. So for part B, you can ignore all information in the left hand side. You can ignore the data in 21 holes. Okay, all of them is negatives now because inside 21 holes we don't have dynamic pressure, only static pressure because we cover it already. Okay, so for part B, we only care about the data in the right hand side. And for part B, we use this table to collect data. Okay, circle, square, diamond, raindrop facing forward and raindrop facing backward. As the data units only in the right hand side. Ignore the 21 holes, 21 blue column. Okay. So the data units for part B is room pressure, room temperature, total force, hydrostatic tube, fan speed. That's enough for part B. Okay. For part B. And for part B, as you can see is data is this document. Okay. We have slide here. Different set without pressure tapping. Okay. I highlight here. You can ignore the blue pressure columns on the left of the screen. So it's the screen. Use the data on the right the screen only. Okay. So for circular cylinder, I give you the data at 3 fan speed, 14, 16, and 1800. So you have to do a 3 fan speed, all of them. It's similar for square, 14, 16, and 18, all of them. Diamond, 14, 16, 18. Raindrop facing forward, 3. And raindrop facing backward, 3. Okay. And for part B, similar for part A, you have the sample calculation here, no pressure holes. And this one is sample calculation for square shape. Okay, it's very easy. Square shape, and it's similar for circle, for diamond, for raindrop facing forward and backward. Okay, this one is sample calculation for square. So that's for part B. Do you have any question for part B? Do you have any question? Okay, you see here. We use the raindrop to cover the cylinder. Okay, this one to cover the cylinder. So now we don't have the 21 holes on the half cylinder is as covered already. So we don't care about the pressure inside the 21 holes. We only care about the force, about the hydrostatic tube and fan speed. Okay. So do you have any question for part B? Any question for part B?
I got a question. Are those shapes 3D printed?
Yeah, 3D printed.
Okay, thank you.
3D. You have any question? Here we have 3. This one for circle, okay, used cover. We have this one is square, and in this side we have a diamond. For raindrop facing forward and backward, we use this one, okay, to cover. Cylinder, we have new cylinder. That's easy, yeah. Do you have any question? Do you have any question? So maybe at this moment you don't have you don't study about external flow, yes, maybe we'll start next week. Okay, so after that, if you have any question about this one, you can email me. Any question? Any question?
So we have how many set of data for part B? I don't remember.
Three for one object. There's only three
Are
for
we
one
do
object.
calculations for the three of each
Yeah,
phase?
for three.
Okay, okay. So I wanted to clarify that. Thank you.
Yeah, you do calculation for three, and I only give you three for part B. Okay.
Perfect.
So it's, any question? You have any question?
No, I think I'm going to review the sample calculations, and then if I have any question, I send you an email, Luke. Thank you.
Okay. Yeah, thank you. So actually, I upload the video for part A and part B on the Canvas already, so you can have a look it and have a look the lab note, the data, the sample calculation is very important, I think. Okay, so it's similar to part A. Sorry, so I'm to experiment 1. In experiment B, experiment 2, you find CD and compare CD. Okay, and after that, you have to show why you have the difference and the reason for the difference and how to improve the experiment. Okay, you can give the idea. It's similar to lab 1. And as I see in the lab report 1, some of you did very well. So I hope that you will have good results in lab 2. Okay. Any question? If you don't have any question, you can move.
Thank you.
That's
no,
enough.
not for now.
Yeah. Okay. Thank you.
Thank you. Bye.
Bye bye. Okay, thank you.